I'm Elizabeth Morrison. I'm an ADHD clinician, coach, and neuroinclusive systems designer, and this is Quirky Apes. My background spans psychology, neuroscience, math, sociology, evolution, organizational development, and political science, which is a lot of ways to say I am extremely interested in how humans work. So let's get into it.
Stimming is regulatory behavior. It is how neurodivergent nervous systems manage internal state, process sensory input, and maintain the arousal balance needed to function. It needs practice during the exact developmental window when the brain is most ready to build it. And when that practice gets interrupted, the costs compound across the lifespan. So, what does stimming actually do? The neurodivergent brain runs on a lower dopamine baseline than the average brain. The system is built differently, which means that it needs to generate its own stabilization more actively than a neurotypical nervous system does. Stimming does that. The predictable, self-generated sensory input of a stim produces small, reliable dopamine signals through the brain's reward circuitry that keeps the system calibrated. The nervous system generates its own dopamine stabilization through repetitive sensory behavior while the baseline runs low. Redirecting stimming interrupts that process at its source. Stimming also works directly on the brain's arousal regulator. There's a spot in the brain that controls alertness and stress reactivity, and it responds to rhythmic input by tuning its own firing rate down. Predictable, repetitive sensory input is one of the most reliable ways to bring a nervous system that is running too hot back into range. And it works in the other direction too. For an under-aroused system, the motor engagement of stimming brings activation up to where it needs to be. One behavior for both directions, self-directed and always available. The serotonin system is also involved. Serotonin pathways modulate anxiety and repetitive behavior, and stimming serves a serotonin-mediated function specifically around anticipatory anxiety. Predictable, self-initiated repetitive behavior reduces the felt sense of threat before it ever arrives. Anxiety is a resource drain, and a nervous system running at a high baseline anxiety has less available capacity for everything else. The brain's excitatory and inhibitory systems also benefit from stim practice. Neurodivergent nervous systems often have less efficient inhibitory signaling in sensory areas of the cortex, which means that sensory input can tip into overwhelm much faster than the average brain. Stimming generates a bounded, predictable excitatory response that the inhibitory system can manage. It is essentially graduated practice from the inhibitory circuits, training them to handle sensory loads in increments the system can tolerate. Removing that practice and the sensory cortex develops with untrained inhibitory capacity. The threshold for sensory overwhelm is then lower, and that gap is structural. The other thing that stimming builds is interoception, which is the body's ability to accurately read its own internal signals. The insular cortex in your brain builds a model of what the body feels like through repeated sampling of felt experience. Stimming generates high volumes of predictable, proprioceptive, tactile, vestibular, and kinetic input, which gives that insula exactly the repeated practice it needs to build an accurate body map. Interoception is the early warning signal. It is how you know you're approaching capacity before you've already blown past it. And there is a developmental window. Neural circuits are built through use. The brain myelinate and preserves the circuits that fire regularly during development. And in adolescence, it prunes the ones that have been sitting most quiet. Myelin is the insulating sheath around nerve fibers that makes signal transmission faster and more reliable. More myelin means faster and cleaner regulatory signals. Regulatory circuits that go unpracticed during developmental windows arrive at adulthood slower, noisier, and oftentimes less resourced. And that is the structural outcome. It's not a temporary outcome. The suppression cost runs even deeper than just behavior. Managing a nervous system without its primary regulatory tool draws on prefrontal resources continuously, resources that are very expensive metabolically and would otherwise go toward learning, social development, and building skills. The prefrontal cortex is, like I said, one of the most metabolically expensive regions in the brain. And that means it's the first to degrade under resource constraint. So asking a child to suppress their stims and then perform at full cognitive capacity is like asking someone to sprint while holding their breath and then wondering why their times are inconsistent. The overhead is invisible, but it runs constantly, and it runs at the expense of everything the child is supposed to be building during those years. And play compounds this further. In early childhood, stimming and play are running through the same circuitry, which means that suppressing stimming suppresses exploratory learning simultaneously. The developmental cost shows up in a pattern of underbuilt skills across multiple domains because the vehicle for building those skills was being redirected through the window when they were supposed to develop. Chronic stress is also a structural cost that accumulates over time. Sustained stress hormone elevation during development reduces hippocampal volume. This happens through a direct mechanism. Cortisol inhibits new cell growth in that hippocampus, and it promotes the pruning of existing connections. So the hippocampus that handles contextual memory, regulatory learning, and the ability to accurately discriminate when a stress response is actually warranted is the thing impacted. It is also one of the primary brakes on the stress response itself. It's responsible for providing feedback to the HPA axis that tells you when threat has actually passed. So when hippocampal volume is reduced, that braking mechanism is now way less effective. The threshold for overwhelm drops. The recovery time lengthens. And the system becomes progressively less able to learn from regulatory experience because the structure that was supposed to encode and retrieve that learning has less capacity to do so. And of course, sleep is a part of this picture as well. Elevated cortisol suppresses melatonin synthesis and maintains hypothalamic arousal, which means it is physiologically incompatible with sleep onset. Neurodivergent populations already have elevated rates of delayed circadian phase, difficulty with sensory sensitivity, and differences in sleep architecture. Chronic HPA dysregulation from suppression stress compounds all of that. And poor sleep elevates next day cortisol, which raises the allostatic load further, which then lowers the burnout threshold, which then generates more stress. And the loop runs in one direction. There are two outcomes to this one origin. Adults whose stimming was limited in childhood usually show up in one of two ways, and the mechanism behind each is the same. Some feel almost nothing from their body until it's in collapse. The brain's interoceptive system, centered in that insula, learned to turn down the signal volume when nothing could be done about it when it was reported anyway. The rational adaptation. It's an expensive one because now the early warning system is offline. The first clear signal they get is the collapse. And then there are others who may feel intensely all of the time with limited capacity to process any of it. The interoceptive signals are coming in at full volume, but the regulatory infrastructure to respond to them never got fully built. Every internal signal becomes aversive and destabilizing because the system has signal without the capacity to act on it. The same person can also move between states depending on how much they're already carrying. When the allostatic load is low, interoceptive signals tend to be manageable or even quiet. As that load increases, the system tips into flooding. And then at extreme load, the dissociative dampening kicks in and the signal is back to quiet again. This is a load-dependent state switching, and it's completely predictable once you have that model. It explains why the same person can seem to have wildly different relationships with their own body across different days, different environments, and different points in their stress cycle. Caregivers were already doing a decent amount of this when they were rocking, bouncing, and carrying infants as a universal across all human cultures. This is what they were doing, and it almost certainly predates modern humans. The rhythm of a walking adult carrying a baby runs at approximately the same frequency that most reliably activates the vestibular system and brings infant cortisol down. The cerebellum uses that rhythmic and predictable input to build models of what sensory experience is supposed to feel like. And it uses these models to filter and to make sense of everything else coming in. A 2013 study found that this co-regulatory effect is bidirectional. So the mother's heart rate drops alongside the infant's during that carry, which means the nervous system built this as a shared regulatory mechanism, running in both directions at once. Caregivers are also doing external stimming for the infants before their infants can do it themselves. The whole developmental expectation is that the child gradually takes that function over and builds an internal version of what the caregiver is providing externally. That handoff is exactly what gets interrupted when stimming is suppressed during the years it was supposed to be happening. The child needed to move from externally provided regulation to self-generated regulation. And the bridge between those two things is the stim. Stim and play are often the same thing, especially for young children. Stimming and playing run through the same subcortical circuitry. Panksepp identified a dedicated play system in the brain, one of 7 primary effective systems that drives exploratory, repetitive, cause and effective engagement with the environment. Spinning objects, repeating sounds, manipulating things in non-standard ways, finding out what a sensory input does when you do it again, that's the vehicle for early learning, and also exactly what stimming looks like in a young child. These were never separate categories. The behavioral framework imposed that separation, and the neurobiology has never supported it. When that behavior constantly gets redirected, the child then learns that the activities that feel most natural and most regulating are the activities that produce correction. That association suppresses the behavior and marks the whole category. Self-directed, intrinsically motivated engagement becomes something that gets interrupted. And over time, the child stops initiating it. The regulatory circuitry that STEM play was supposed to build goes unpracticed, and the whole category gets associated with being redirected in the process. So many autistic adults find it genuinely hard to access play, and many of the same people find it hard to access STEMs. The same problem from two different angles. The play that gets damaged is that self directed, intrinsically motivated, sensory kind of play that requires no partner, produces no external product, and oftentimes looks very unproductive from the outside. That is also the kind that builds internal locus of regulation, because it is the only kind where the child is both generating and managing their own experience simultaneously. Special interests tend to survive the broader suppression because they often can look respectable from the outside, especially if it's hobbies or expertise or productive knowledge acquisition. They are also STEM play. The regulatory function is identical. And this is also why restricting or pathologizing special interests carries its own developmental costs. For many neurodivergent children, the special interest is the one remaining STEM play outlet that made it through intact. And removing it removes the last functional bridge to self regulation. Children can hit full regulatory exhaustion at the same mechanistic intensity as adults. That means children can burn out. And the conditions children are managing under are often more demanding. The prefrontal cortex, which does the heavy lifting of suppression and reaches full maturity in the mid-20s, is still developing throughout childhood and adolescence. The child is suppressing with a less developed tool in environments they are required to stay in for a majority of their waking hours. And they're there under conditions where the adults around them interpret a regulatory behavior as a discipline problem. What shows up often as school refusal or after school dysregulation, temporary loss of previously acquired skills, or being completely different at home than at school, that's a nervous system that has been managing at capacity all day long, and it just has nothing left. The after-school restraint collapse is a particularly clear example. The child holds it together all through the school day and then falls apart the moment they get home, somewhere that they finally feel safe enough to stop suppressing. That suppression backlog releases all at once. And treating that behavior as a problem adds to the regulatory load rather than addressing what is actually happening. Children also have no vocabulary for what's happening to them. The language for burnout, for regulatory exhaustion, for the cost of sustained masking is barely available to adults. A child experiencing it has no framework at all, which means the only signal they can send is behavioral. And then that signal gets misread. Then there's the adult picture. Adults who had limited STEM access during childhood more heavily rely on external regulation to stay functional. Specific people or specific environments, specific responses, and specific routines end up doing from the outside what the internal system wasn't given the developmental conditions to build on the inside. The external scaffold that was supposed to be gradually internalized remained external because the internalization process had less to work with, relying on co-regulation presence and needing particular environmental conditions to function, maybe struggling to regulate in novel or unpredictable situations. These are the logical outcome of a developmental process that had a core missing component. Many autistic adults also report reduced access to stims or an inability to identify their stims, which maps exactly onto what the suppression history would predict. The behavioral vocabulary for self-directed sensory regulation engagement was suppressed. The categorical associations were damaged, and the skill went unpracticed during the window that it was supposed to develop. The adult trying to find their stim as a recovery practice is working against an active learned association that says this category of behavior belongs to other people. The burnout threshold sits lower then because the regulatory buffer is thinner. The path to burnout moves faster because interoception, which is your early warning signal, was undertrained. And when burnout then arrives, the tic threshold drops because prefrontal suppression capacity was doing double duty, managing both the underlying regulatory motor drive and the ongoing demand load. It eventually runs out of resources, and the system expresses through whatever pathway requires the least effort. Tics and stims share basal ganglia circuitry and the same underlying motor drive. The difference between them is volitional control. The prefrontal resources that maintain that volitional control are exhausted, and that drive expresses then involuntarily in tics. The tic that arrives then at burnout is the stim with voluntary control totally removed. So, finding, protecting, and expanding STEM access is building and maintaining the regulatory infrastructure that everything else depends on. In children, that means protecting the developmental window while the brain is still constructing the circuits that will carry that regulatory capacity into adulthood. In adults, it means recovering access to something that was interrupted, which takes real work against well-established, learned associations. The nervous system retains plasticity across the lifespan, and the regulatory capacity that comes back from that work is real. It's worth the work.
That's it for today, and if you or your organization could use an LPC, coach, consultant, or if you need some training from someone who thinks like this, I'm available at creativesolutionscoaching.com or on all of the socials.